All right, we're going to begin our discussion on entropy with a bit of a conceptual discussion of what entropy is and what it is not. Most students, when they first learn about entropy, get taught that entropy is disorder. And although thinking of entropy as disorder or randomness is not incorrect, it doesn't tell the full story. And so today's lesson is going to be a bit more conceptual, but I want to dispel a couple of the misconceptions about what entropy is and what it is not. So to do that, we're going to look at a few different models. And we're going to begin with the idea of a mixing model. And if you think about a beaker of water, all right, and so what I have here in this 3x5 square, there are 15 boxes. I have 12 boxes that each contain one water molecule, and in the top 3 boxes I have one dye molecule. And if we think about when you first drop a bit of food coloring into a beaker, how initially all the dye is sitting there right at the top. And over time, if you watch the beaker, you start to see the dye molecules float down, and eventually as it mixes together, the entire solution has turned the dye color. So we're going to use this model and talk a little bit about probability and the Boltzmann distribution and link that back to the idea of entropy. So let's look at our initial state here. All right, when dye is first added to the container, the dye molecules only occupy the top layer of the boxes. All right, so each of these dye molecules are indistinguishable from each other, and each of the water molecules is indistinguishable from each other. But if we say, all right, these 3 dye molecules are confined to the top layer of the boxes, the top layer of our beaker. And if we look about how many different ways can we arrange these 3 dye molecules? Now, since they are indistinguishable, and there's only 3 boxes, there is only one possible arrangement. And in terms of the ways or the arrangements, we're going to call that W. Now, the number of distinguishable molecular arrangements for the 3 dye molecules, and the dye molecules are going to be the solute in our solution. That's going to be W, and there's only one way to do it, and that's going to equal 1. There's one arrangement here. Now, if we confine the dye molecules to the top, all the 12 water molecules are confined to the bottom 12 boxes. And so there's only one way, W, for these identical water molecules, and water is the solvent here in our solution, to be arranged. So I have 2 terms here, W solvent equals 1, and W solvent equals 1, so solute and solvent. So if I look at the entire system, how many different ways, if I confine the dye molecules to the top, are there to arrange all of these molecules, all 15 molecules? I would take the ways of the solute times the ways of the solvent, so that would be 1 times 1. And so there is one way to arrange our system here. This is going to be our initial state. All right, so keep an eye on this value for W. Now, as the dye molecules start to mix with the water, some of these dye molecules can start to move down to the next layer. And those that leave the first layer are going to be replaced with water in the first layer. So here, if we now say, all right, the dye molecules are no longer restricted to the top row, but now can occupy any of the boxes in the top 2 rows, the top 2 layers. And again, each box has to have something in it, either a dye molecule or a water molecule, solute or solvent. And so here, if I look at how many different ways can I arrange these 3 dye molecules in these top 6 boxes, right? And so I can have all three in the top. So that's one way. I can put all three in the bottom. That's another. I can put one here and two here. That's a third. So I can go through all the different permutations, and what we would find is that there are 20 different ways to arrange these three dye molecules in the top 6 boxes. At least 20 distinguishable ways to arrange them. So in this case, allowing movement between 2 layers, my W has gone up. Now similarly, there's going to be only one arrangement for the 12 identical water molecules in the remaining boxes. And so again, my W for the solvent is going to continue to be 1. Therefore, I calculate my new W for my system, and we're going to have 20 times 1, and so the ways have gone up to 20, like this. All right. Now we can continue to go through this process. So as the dye molecules continue to mix with the water and being confined from 1 layer, then to 2 layers, then free to move into 3 and 4, and then finally to all 5 layers, we can calculate all the different ways to arrange our solute. So like I said, there's only one way to do it if they're confined to the top layer. There's 20 ways if we confine them to the top 2 layers. There are 84 ways in the top 3, 220 ways to arrange them in the top 4, and if the dye molecules are allowed to go to any of the boxes in any of the layers, we're going to have 455 unique distinguishable ways of arranging those dye molecules. And so as the ways of distributing the solute are going to increase, the ways of increasing the system are going to increase. As the W increases, the entropy of the system is also going to increase. Entropy is really about probabilities, and the universe in general wants to increase the possibilities. It wants to increase the entropy of a system. Now, could you make the argument that the mixed dye, where the dye is throughout the whole beaker, is more disordered than if it was confined to the top? I guess you can make that argument that there is a increase in disorder, but really what entropy is about is it's increasing the possibilities, increasing the value for W here. All right, now let's look at a different model. Let's look at the osmosis model. Now, so if you recall from Gen Chem 1, we discussed osmosis with colligative properties. And we said if I have a semi-permeable membrane separating 2 sides of a solution. So on one side I have water, and on the other side I have a mixture of water and solvent. I can have water passing back and forth across this membrane, but I can't have any of my solute particles passing over here. And what osmosis says is that the solvent is going to travel in a direction so as to try to equalize the concentration on both sides. So in this case, we would expect water to want to flow from the less concentrated side to the more concentrated side in an effort to try to dilute up the more concentrated state on the right. Well, if we look at osmosis in terms of the probability, right, and so using the model we just discussed with what's going on over here, right, and look only at the solvent molecules, we can see that on the left there is only one way to arrange those solvent molecules on the left. All right, all 9 of these water molecules are indistinguishable. Now over here, again looking at the solvent system, I've got 3 dyes in here, and we would see that there are 64 ways to arrange these three dots, and hence the whole system over here on the right-hand side. Right? Actually, not 64, that's going to be 84. Sorry. So there are 84 ways to arrange the three dots in the 9 boxes. So initially, looking at the system, right, the W of my solvent and the W of my system is going to be 84. Right? That's going to be our initial state here. Now, knowing that the solvent's going to want to flow from the less concentrated side to the more concentrated side, right, so the solvent's going to flow across the membrane, I'm going to take one layer of our water and move it over here to the right. So this is going to represent the later state after osmosis occurs. Now, looking in terms of the probability, right, on the left-hand side, there's still only one way to arrange those solvent molecules. Over on the right, though, now that I've added more solvent, I've got a whole other layer of boxes. Those dye molecules have more possibilities, more places where they can go. And in fact, if they have 4 layers to play around in, they're going to have 220 different arrangements. So looking at the total system here, there's going to be 220 ways of arranging the solvent. So from the initial state here, where there was just 84, to having the water flow to this other side, I have increased the entropy of the system. I have increased the W. And so that's why the spontaneous thing is for water to flow this way. It increases the entropy, increases the W. All right, now let's really take a look at heat now, because this is where entropy is really going to come into play. All right, the way we're going to do this is we're going to look at 4 atom objects. Each of these blue circles represents an atom. And so thing number 1 is going to have 4 atoms. Thing number 2 is going to have 4 atoms. Now we're also going to say this: adding energy to an object, to one of these things, is going to increase its energy content. And that's going to produce an increase in temperature. Just as removing energy from an object increases or decreases the energy content, and that's going to produce a decrease in temperature. So let's say that thing number 1 here is going to have 4 quanta of energy, right? So we just want to quantify how much energy thing 1 has. And so we're going to say thing 1 has got 4 energy, and thing 2 is going to have 8 energy. Now this means that thing 2 has more energy, and it's going to be hotter than thing number 1. Now let's diagram this using the probability models that we have been using so far. All right, so I've got atom 1, 2, 3, and 4 here in one of our things. And in this column along here, we're going to say how many energy quanta these atoms have. Okay. Now, if I don't have any quanta of energy, right, and I'm going to represent a quanta of energy as just a halo, a little circle around one of the atoms. If I don't have any energy here, each of these 4 atoms is indistinguishable from the other one. And so that way, in terms of arranging that, there is only one way of arranging these atoms. 1, 2, 3, 4. They're all distinguishable. If I swap 1 and 2, that's still the same arrangement. Although here's what I'm going to do with an energy quanta. Right? Let's say I'm going to highlight and put an energy halo around atom number 1. Okay. Now, if I have one energy halo to distribute amongst these 4 atoms, how many ways can I do that? Well, I can put it around atom number 1. I can put it around atom number 2. I can put it around atom number 3. Or I can put it around atom number 4. All right, I've only got one halo to distribute. But if I have one quanta, right, the number of ways of distributing that one quantum of energy is 4. 1, 2, 3, 4. Now, if I have 2 energy halos, right, I can put one around atom number 1, and I can put one around atom number 2. All right, that's one way of distributing them. I could also say this, I can put both of my energy halos around one of the atoms. That's a second way of doing it. And so I can continue on and to say how many different arrangements can I put 2 halos around. And so if I go through all those possibilities, I would find that there are 10 different ways of distributing 2 energy quanta. And so I can make a table here depending on how many quanta I have. And so if there's no energy, no quanta, I can arrange those 4 atoms one way. If there's 1, I can distribute it in 4 ways. If I have 2, there are 10 ways. 3, I can do 20. And I'm just going to go ahead and write these numbers in here. The more halos I have, you can see how the number of possibilities is going to increase. You have 84, I have 120, and if I have 8 to distribute amongst 4 atoms, I can do that 165 different ways. All right. So again, as I increase the energy, I'm increasing the possibilities. I've got a number of different ways to distribute that energy, and it just continues to go up here. So now let's go back to our initial idea here. We said that thing number 1 has 4 energy quanta, right? And so the W here with 4 quanta is going to be 35. And thing number 2 that has 8 energy quanta is 165. So if I look at the initial system here, how are these 2 atoms distributing their heat? I would take the 35, multiply it by the 165, and we would see that there are 5,775 ways that these 2 objects can distribute the heat that they have within them. Okay? Now, let's do this. Let's now bring these 2 objects to where they're in contact with one another. I've got a hotter object in thing number 2, right? It has more energy, it's at a higher temperature, and I'm going to bring that in contact with thing number 1 that had fewer quanta, fewer energy. Now, we all know if you take a hot object and you put it in contact with a cold object, heat spontaneously wants to flow from hot to cold. And so if I bring these 8 atoms all together, the way that the heat's going to flow is it's going to try to take that total of 12 quanta and it's going to give 6 to thing number 1 and 6 quanta to thing number 2. So now when I look at, well, how many ways can these 4 atoms distribute 6 quanta? Well, it's going to be 84 here. Now thing number 2, it has less quanta than it had before. So it's going to distribute those 6 halos 84 different ways. But let's look at the overall system now. Right? We take the 84 times 84, and we'll see that there's a total of 7,056 ways that now these atoms can distribute their energy or their heat. And so the W has increased. This has got a higher entropy. And that's what the universe naturally wants to do, right? And so that spontaneous flow of hot to cold to distribute or spread out that heat has increased the entropy, and that's the natural order of things. Now, can I make a disorder argument with this? I think that's a little harder to do. All right, I've increased the possibilities, but I don't know that I've necessarily increased disorder. I've just increased the ability to spread that heat out. And that's a better definition of what entropy is. It's the idea of heat naturally wanting to spread out. And the second law of thermodynamics says that heat, unless it's hindered from doing so, naturally wants to spread out. And so that's what we're doing here by increasing the distribution of those energy halos through more atoms, right? So that's a better idea of entropy. And next time we're going to talk more about conceptually what happens with entropy when we change temperature, when we mix things, when we start increasing the number of particles. And there you're going to see disorder coming into the discussion a little bit more, but I want you to kind of push aside the idea that entropy is disorder and think about entropy as more of possibility and increasing number of energy states. That's just a better way to look at it. All right, that's it for today.